Okay, 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 okay. So if you join the class, just wave. We would be starting once I see 5 waves. So let's do that quickly. Class is actually live and going on. You might not be hearing any sound, but the class is live. So 5 waves, and we start the class. So if you join the class, just wave. We will be starting once I see 5 waves. So let's do that. Class is actually live. Okay. Okay, I don't think we'll have to be waiting for want of time. We would have to like get into it so that we would finish in time and everybody goes about their normal business. Let me just put on yeah, where is it? Where is this thing again? Okay. Okay, so basically that. So welcome everybody to the class. We are going to be quickly getting into it and then taking this study as systematic as possible so that we'll be able to cover as many things as possible. I probably um in the last class we studied things about IPAC nomenclature, but in today's class we are going to get into the different homologous series so that we'll be able to finish in time. Now, with that said, we are going to be discussing for today the halo organic compounds, and then once we are done with that, we will now get to discuss your isomerism basically. And with that said, The major things that are being talked about in every homologous series, they are just like about 5 major points. The first thing you need to take note of in a homologous series is more like the classes that are found in that homologous series. After you consider the classes, you consider the IUPAC nomenclature for that homologous series. After you've considered the IUPAC nomenclature, you consider reactivity. Reactivity is what are the things that makes that particular substance reactive or non-reactive. Then you get into the other aspect, which is lab preparation of different compounds in the homologous series. Now, after discussing that, you now get into the different properties, that is physical reactions and the physical properties I meant to say, and the chemical properties, which have to do with the chemical reactions basically. And if you are done with the chemical reactions, you talk about the uses, and these are the major things that you need to know for each of these homologous series. So for today, we are going to trash the haloorganic compounds, and after trashing that, we'll now get into isomerism. Isomerism is a study we should have taken earlier on, but I want to just delve into a homologous series for today and then run off through isomerism basically to help us understand that better. So let's get into it. The first thing I would like to say is that the halogen group basically consists of your group 7 elements. As everybody should know, your group 7 elements are the elements basically. Examples are the fluorine, chlorine, the bromine, and the iodine. These are your major group 7 elements. There's the acetane, but these are the ones that we're going to be considering. Did you notice something about the halogens, that the spelling of their names actually end with INE? So these are like simple factors that can help you note what are halogens. So when a halogen is attached to an organic compound, that is what we refer to as a haloorganic compound basically. In some cases, you might be referring it to as halogeno compounds. Some other textbooks might just tell you that they are halides or organic halides basically. So, but the point about it is that for you to talk about a haloorganic compound, you are considering the presence of fluorine, chlorine, bromine, and iodine basically. With that said, we would get into it straight up. The first thing we are going to talk about are what are the different ways in which haloorganic compounds can be classified. Now, the first classification is based on the number of the number of halogens that are found in the organic compound. The first classification is based on the number of halogens that are found in the organic compound. Before I continue, so far I hope you guys are following in the class. Those of you live, hope you're following. Yeah, I forgot to say this though, but if you want to ask questions, for those that have not been to the class before, you ask questions by typing. You can't, there is no scenario where you auditorily ask your questions basically. So you type in the questions when you have confusions. Okay, so let's get back to the screen. Now, as I was saying, there are different ways of classifying compounds, but the first way we are going to consider is based on the number of halogens existing in the compound. Okay, now based on that number, you could have mono, halo, or monoorganic. Okay, I presume the internet has been restored, so let's continue. The monohaloorganic compounds, basically, as the name implies, contain only one halogen. So anytime you are considering a monohaloorganic compound, it contains only one halogen. Now, this monohaloorganic compound can actually be split into 3. You have your primary, your secondary, and your tertiary. So whenever you are talking about your monohaloorganic compounds, they can be further split into primary, secondary, and tertiary. And it's important you note this or have an understanding of this basically. Now, for those of you that followed my study or had the first class with me, you would remember in our introduction we talked about the classes of carbon. So I'm going to do like a revision of that, because that is what is going to help us understand this concept well. A revision of the classes of carbon. Okay, so imagine we have numbers 1, 2, 3, 4, 5, 6, 7, and 8. Now, in the classes of carbon, the primary carbon is the carbon atom that exists terminally, and it is attached to only one carbon atom. So number 1, number 6, number 7, and number 8 and number 5 are primary because they exist at the end, and beyond that they are directly attached to only one carbon atom in the chain. That is what makes this primary. So if we are to indicate them, this is primary, this is, okay, sorry, trying to get it, yeah. So if we are to indicate them, as I said, this is primary, this is primary, this is primary, this is primary, this is primary. Why is it primary? Because it is at the last carbon atom in the chain, and then secondly, it is only directly attached to just one carbon atom. So you have that. Now we go to the next one, secondary. Secondary carbon atoms are the carbon atoms that are directly attached to only 2 carbon atoms in the chain, and you notice that that is carbon 4. So this is secondary. Why is this secondary? Because there is only 2 attachments of carbon on both sides. In this case, this one has 3, 1, 2, and 3. So this is not going to be tertiary in any, sorry, secondary in any way. This is instead going to be tertiary. Why? As I said, primary just 1 carbon atom, secondary 2, which means tertiary would have 3. So tertiary carbon atom would have 3 carbon atoms directly attached. Tertiary, yeah, tertiary, sorry. So tertiary would be indicated here. Tertiary, that is carbon 2 is tertiary. And then finally we have the quaternary carbon atom, which is the one attached to 4 different carbon atoms. Now, the indications of the positions of this carbon atom will tell us the class of haloalkane. When a halogen is attached to a primary carbon atom, it becomes a primary halogen. I take it again. If a halogen is attached to a primary carbon atom, it becomes a primary halogen. So as I said, monohalo organic compounds are classified into primary, secondary, and tertiary. So in a scenario where you have a halogen attached to any of the primary carbon atoms in the chain, it becomes a primary halogen or halogeno compound. Okay, let me explain. As I said, list out the halogens. We have chlorine, fluorine, bromine, and iodine. So when any of these guys are attached to the primary carbon atom, so if I put my chlorine here, automatically this is a primary halogen. Those that are still online with me, I hope this is clear. There is a little lag with the okay, good. I presume it was resolved, like the initial issue, right? There was an internet issue, but I hope it's clear wherever you are. Those of you still online, hope it's clear so I can continue. There was a little disconnection, but hope it's done, like you're following. Okay, I'll just have to continue. Oh yeah, okay, no worries. So let's continue. Now, sorry about that. Where was I? Yeah, back to the board. So I was saying that if you attach any of these halogens to a primary carbon, it automatically becomes a primary halo organo compound or a primary halogeno compound. Now it's important you take note of this because we are going to be referring to this when we get to our reactions. You get, especially the nucleophilic substitution that occurs in your haloalkanes generally, or halogeno compound. So it's important that you note these things, because if you don't, probably you have confusions when we are discussing the reactions. Okay, now secondly is, I presume that all of you went through the study on order of reactions that I put out to the group. It's important because we are going to be using that principle in our discussion of the SN1 mechanism and the SN2 mechanism. They are basic principles anyway, but these are like things you need to understand before you get to understand them, those mechanisms. Okay, so back to you guys. Now, as I said, once you have that any of these halogens is attached to a primary carbon atom, any of the primary carbon atoms, it could be on number 5 as we initially had, it could be on number 8. This is a primary carbon atom, and which means that this compound is now going to be referred to as a primary halogeno compound. So just have that in mind. Good. So moving ahead, I presume that with this you can understand the secondary. It means that the secondary halogeno compound is a compound in which the halogen is attached to a secondary carbon atom. Basically, you have that, which means a tertiary halogeno will now be a compound in which the halogen is attached to a tertiary carbon atom, and you have that basically. Now, once you are able to understand this will help us when we get to our, because these classes of halogeno compounds will determine the type of substitution that will occur to them when we get there. So it's important you understand these classes. So I review it again. Primary halogeno is a situation where the halogen is found on the primary carbon atom, which I told you exists terminally. Secondary halogeno is a situation where the halogen is found on the secondary carbon atom. This is the secondary carbon atom for this case. In this case, so if I put a halogen in this case, what this is referred to as at this point, okay, without the bromine, at this point, this is going to be referred to as the secondary halogeno. You get? One of the reasons I'm talking about this is because you could be asked what type of nucleophilic substitution mechanism occurs in your secondary halogeno organic compounds. The answer is SN1 and SN2. We'll discuss that when we get there. Okay, so moving ahead, we go to the next one, and the next one is a situation where you have a tertiary halogeno compound. Tertiary halogeno implies that the halogen could be anything: fluorine, bromine, chlorine, iodine, anything. Once it's attached to a tertiary carbon atom, it becomes a tertiary halogeno. And that is, or these are the main points that should be talked about in your mono halogeno organic compounds. Now, remember I said this classification is based on the number of the number of halogens present in the organic compound. Okay, so after mono, I guess you should know what should follow, and that should be di. Now your dihalogeno, or dihalo organic compounds implies that there are two halogens. Usually they have to be two halogens of like two similar halogens. They have to be the same halogens for you to use this principle I'm about to apply. Now listen, in dihalogeno, basically the important forms of dihalogeno compounds that you can have are your germinal dihalides and your vicinal dihalides. So imagine you have a chain of carbon atoms, 1, 2, 3, 4, and you have a dihalide, meaning that there are two halogens, so chlorine and chlorine. Once you have a situation where the two halogens are placed at adjacent carbon atoms, when you say adjacent, it's one after each other, so this carbon, the next carbon. So once the halogens of the dihalide are placed on adjacent carbon atoms, they are referred to as vicinal dihalides. So this is adjacent. Oh, the spelling, this is supposed to be GE, not GER. That's like germ. This is germinal, not GER. Okay, so this is for adjacent. So once you have that the two halogens present, which makes it a dihalide, are placed on adjacent carbon atom, what this is referred to as is a vicinal dihalide. You get, just have that in mind. So it's more like a 1, 2, or 2, 3, or 3, 4. Once it is adjacent, automatically you refer to this as a vicinal dihalide. Okay, those of you in class, okay, I hope this is clear. Yeah, hope no issues. One response and I continue. Yeah, you've not watched the order of reaction. Don't worry, I will just do a brief description when we get there. Yes, but hope you are following the class. Okay, makes sense. So moving ahead. Yeah. Okay. So moving ahead. Yeah, where was I? Okay, so I was saying something. I said that once is adjacent, is vicinal. Now the germinal dihalides are basically when you have the halogens on the same carbon. when you have the halogens on the same carbon, maybe 1 1 2 2 3 3 4 4 5 5, any once is on the same carbon is germinal. So this is vicinal. But if I have a chain of carbon atoms like this and the halogens are on the same carbon, this is now what we refer to as germinal. Okay, so it's important to take note of these things because these arrangements will affect the reactions that we're going to be considering further. Now, the point I would like you to note is that this arrangement also applies to your alcohols, which means when I say a vicinal diol, what I actually mean is an alcohol in which there are two hydroxyl groups and they are placed adjacently. If I say germinal diol, it means I have an alcohol in which the hydroxyl group are two and they are existing on the same carbon atom. So just have that in mind. The term germinal dihalide indicates same carbon, while vicinal dihalide indicates adjacent. It also applies to alcohol. So just have that in mind as we are going further. So that's that about your dihalogeno. We move ahead to the next one, and basically these are the two most important ones anyway. Based on the classification of number, there is trihalogeno, tetra, polyhalogeno, you get, but that is based on number. Now, the next one we are going to consider is classification based on the level of aromatization, where you have your aryl halides and your alkyl halides, basically. So in the aryl halide, once you are considering an aryl halide, it means that it is attached to a benzene ring. The aryl group is the benzene ring group. So once you have benzene ring attached to a chain of carbon atom that has a halogen or directly to a halogen, this is what we refer to as your aryl halides. Very important thing to note about your aryl halides. Sorry, aryl, not, yeah, your aryl halides. Your aryl halides are more prone to what we refer to as electrophilic substitution. So just take note of that. We are likely to discuss that eventually, but just have that in mind that the form of substitution reaction that occurs in your aryl halides are your electrophilic substitution. But in your aliphatic halides, specifically your aliphatic saturated halides, what type of substitution, the type of substitution that is characteristic to it is your nucleophilic substitution. So this classification into aryl halides and your aliphatic halides is strictly dependent on the aromatic or presence or absence of the benzene ring. Let's use that. So once there is a benzene ring, is the aryl group, and the type of substitution reaction characteristic to it is electrophilic. We are going to discuss these things in detail, so don't bother about this description yet. Just take note of it that in aryl halides, the form of substitution that occurs or is characteristic to aryl halides is electrophilic, while in the case of aliphatic, you have your nucleophilic substitution. As I said, we are going to discuss these things in details. Now, having mentioned this, we would have to move it up a notch into the next part of the study. Originally, the next part of the study should be nomenclature, but we have treated naming off. We have dealt with that. So I'll just give you two questions just to joggle your memory. As I said, remember, consider the different classes, talk about the nomenclature before you go into possible reactivity properties. Then you get to discuss the different lab preparations, the different reactions, physical properties, and then we get to uses and call it off there. Now, so just to check your memory, did you try naming this particular compound? So imagine you have this particular compound. Okay. Okay. So I would like you to use the UMP system to name these guys. Use both the UMP. This is number 1, number 2. Yeah. Remember, just point to note is methyl. Once you have your methyl, that's methyl benzene is basically toluene. I'm just saying. Okay. Okay, yeah. So attempts naming this compound, basically number 1, number 2, and number 3. Let's make it a little bit tricky. Yeah. Okay, so quickly do that. I'm expecting your answer. Quickly do that. Send out your answer. Number 1. Write the name. I'll prefer you use, okay, you could put number 1. You write the normal numerical system and the UMP system. Any one of them I would accept. So put out your names or the answers. Okay, number 1 is 1-bromo M-chlorobenzene. Okay, makes sense. But why did you start from? Okay, go ahead. Okay. If you join the class, it's important to indicate your presence. So just wave for those of you that just joined the class. Okay. So I'm giving you like 2 minutes or so. Just get your answers ready. Okay. Okay, I think I'll have to come in. So let's Kaibapi also. There's no time. Okay, so yeah, you said yeah, your first answer is 1-bromo M-chlorobenzene. Makes sense. Okay. 2-1 chloro. 2-1 chloro. Where is 2-1 chloro? Oh my god. Okay. Iodotoluene. Okay, sorry, number 2 is 1-chloro or iodotoluene. Okay. Prey said is 3-bromo 1-chlorobenzene. Okay, good. I like the fact that there's a little bit of discrepancy here so that I will be able to clarify this. Now, to clarify this is very simple. Let's look at our screen. First of all is when you are using the numbering system, when you notice that you have both of them are halogens, you are supposed to either allocate locant number 1 here or locant number 1 here because they are the same functional group. So what do you consider when you have different halogens in the same chain? You consider the spelling. Once the distance is the same thing, what you should start numbering from is bromo. That is, you consider spelling. What I actually mean is this. Imagine, for instance, you have this. Here you have bromo, and here you have chloro. If you notice, the distance to a substituent is equal, and both of them are halogens. So which means they are the same functional group. because they are the same functional group and their distance from the terminal carbon atom is the same thing, the next thing you are going to consider is the spelling. You will now check bromo starts from B, chloro starts from C, which means it's better to have one bromo and maybe this is 1, 2, 3, 4, 5 and 5 chloro than to have 5 bromo and 1 chloro. It doesn't really make sense because the alphabetical order. Once you notice that they are both halogens and the only substance are halogens, and you need to start numbering from, especially in an arene, you start from the halogen of the lowest alphabet. What I explained, is it clear? Is it clear? Is it clear? What I just described, is it clear? Hope what I explained is clear so I can move ahead. Hope it's understood. Yeah, what I explained right now, is it okay? Makes sense. So let's continue. Now the implication is that we would now have to give bromo number 1. And if you count number 1, 2, 3, 4, 5, this will be 5. Come on, it doesn't make sense to count like this, which means we have to count in a way to make sure that it has the lowest possible number. So that means we're going to count number 1, number 2, number 3, number 4, number 5, number 6. Now, according to our OMP system, number 1, 2 is O, which is ortho. 1, 3 is meta. And then 1, 4 is para. So the name of this compound is either going to be 1 bromo. You know, number 1 has no, like in the OMP system, number 1 has no different name. So it's going to be 1 bromo and 3 chloro benzene, or 1 bromo. Now instead of saying 3, we have it on the metacarbon, so it's going to be M chloro benzene. So I guess yeah, Kachi, I think Kachi, okay, Kachi should be correct. Yeah, Kachi, you're correct, basically. So yes, with that, Kachi is correct in the first one. So moving ahead, I hope, praise, clear. Okay, let me try re-explaining praise. So look at this thing. Consider this particular guy now. You know, normally, if you are going to give number, let me just draw it in the normal way so that you don't go confuse anybody. You have chlorine, you have bromine. If you are going to give number, normally, if it was like this, we will say that the substituent is closer from this end to bromine than chlorine from this end. So if you are counting, this will be 1, 2, 3, 4, 5, not 1, 2, 3, 4, 5. But in a situation where you now have 2 halogens and the ends are equal, if you count from here is 1, if you count from here is 1. So where are you going to give number from? Are you going to count 1, 2, 3, 4, or count 1, 2, 3, 4? What you actually check at this point is no longer, because both of them are halogens, you are not going to consider higher functional because they are the same functional group. So what you are going to consider to know which one you start counting from is the spelling. Start counting from the side where you have a lower, like the first spelling. In this case, that means bromine is smaller than chlorine in alphabetical order, which means you're going to start from the side of bromine. Which means that the correct order of numbering, because bromine, which is B, you have B and Cl, you check B is lower, so I'm going to start counting from the side where B is lower. Why? The 2 of them are both halogens and they are at equal distances, so I need to count from the side closest to bromine. That's what happened here. We would have given chlorine number 1 or given bromine number 1. But because bromine has a lower alphabet, we are going to give it number 1 because the 2 of them are halogens. If it was hydroxyl or some other thing, we wouldn't be considering that. I hope is it clear now? You okay? Praise? Clear? Praise, is it clear? Praise. Is it clear? Okay, yeah, okay, makes sense. So let's move ahead. Now, having said that, we go to the next compound. First of all, we already know that, or we should already know that this is toluene now. Once you see benzene and methyl, is toluene. I told you that if there are 2 methyl groups, is xylene. This you should go and review. If for instance you've forgotten those things, go and review them, because they would follow us all throughout the study. Now, having mentioned this, the next thing we are going to consider in this case is the fact that numbering, obviously toluene, the main guy is toluene now, which means the number one guy, methyl, has to be above in this case. So which means we are going to give this number 1, number 2, number 3, and number 4, because toluene is the major organic compound. So because toluene, what makes toluene is the CH3. Without this CH3, this is not going to be toluene. That's why we are considering him first. So with that said, we are going to give this number. So having said this, we'll have that the numbering system, this is going to be, the parent name is toluene, not methylbenzene. You can say methylbenzene, but don't say methylbenzene. The parent name is toluene. I mentioned this in the last class. So this is going to be, chlorine is going to come first. So that's going to be 3-chloro 2-iodo toluene. The other way to name it is, this is 1, 2 is ortho, so O, meta, and para. So which means this is going to be chlorine first now. So M-chloro and O-iodo toluene. Okay, so yes, let's see who got the answer. Yeah. Okay, yeah. Who even gave the answer? Oh, yeah. 1-chloro. Yeah. Is it 1-chloro? It's not number 1 now. Like, you get the point now. I hope this is clear. For praise, I think, who answered this? That's Kachi. For Kachi, I hope this is clear, that if you are considering the toluene, the major okay, sorry, I hope it's back because it's disconnected. Okay, now let's move ahead. For want of time, we'll name the other one and call it off there. Okay, so then in this case, we move ahead. This is carbon, 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 carbon. So if we are counting, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, which makes this an octane. And because this is an octane, this is going to be 3-chloro. Oh no, bromine first. The substituents here are bromine, chlorine, and ethyl. So this is going to be 4-bromo, 3-chloro, 4-ethyl octane. Okay, so let's review our answer. 4-bromo. Oh, is that? Oh, yeah. 2,3-dichloro. I missed that. 2,3-dichloro. Yeah. So this is like 2,3. I missed this chlorine here and this chlorine here. Okay, yeah. So basically, we've done this. I'm just trying to remind us of the study we had in our earlier class, basically. But I hope there is no confusion from Praise. Praise. Hope there is no confusion. Okay, I would like to move ahead. That's what I'm asking. If it's all clear, I think we would have to move ahead. Just one answer, please. Praise. Make I re-explain. Do I need to re-explain it quickly? If you need me to re-explain, just indicate. Yes, I'm waiting for your answer. Abi, make I just continue. Okay, I think I would have to just continue basically. Now, okay, re-explain. Okay. Let me just take everything out. Take everything out and take it again. Now, we had something that looked like this. 1, 2, 3, 4. 1, 2, 3, 4. And then here, we probably had this and then this. Right? And then here we had I think it was bromine that was here. Here we had chlorine, and also here chlorine. But this went like this and like this. Okay, so we are to name this compound. The first thing you need to note is that at every end and at every junction, you introduce a carbon atom. So carbon dey here, 1. Carbon dey here, 2. If I make I use different color, you understand? Make I use different color. Make I use different color. So carbon dey here, 1. Carbon dey here, 2. Here na junction na. Here na another junction. Carbon dey there. C junction here. Carbon dey here. C junction. Carbon dey here. But this end bromine there, so we won't put carbon. Junction. Carbon dey here. Junction. Carbon dey here. Carbon dey here. End. Carbon dey here. End. Carbon dey here. Now, our longest chain of carbon atoms that is continuous is 1, 2, 3, 4, 5, 6, 7, 8, which means the parent name is octane. Now I would like to circle out this parent chain so that it will not be confusing when we want to see our substituents. Oh yeah, so circling it out, we have this. See your substituent. Your substituent is 1, 2, 3, and 4. It's clear. What do? You give it number now. So let's give it the number as we should. Number, we'll start from here now. Here is closer. So 1, 2, 3, 4, 5, 6, 7, 8. So let's now put out our different. We have chlorine. Chlorine is a substituent. The other substituent is bromine. And then the other one is 2 carbon alkyl group is ethyl. Arrange it alphabetically. Bromo comes first, chloro second, and ethyl last. So which means if we are going to name this compound, we'll start naming from bromo. Where is bromo attached? It's number 4. So 4 bromo. And after bromo is chloro. Chloro day number 2, chloro day number 3. So it's 2,3 dichloro. 2,3 dichloro. After chloro, there's no other chloro, we go to ethyl. Ethyl is on number 4. 4 ethyl octane. So basically that's that. If you might actually need to go and review our last week's study on naming, it will really help you a lot if you haven't. Okay, so that's that basically. I don't want to emphasize this because I want to majorly discuss the reactions we have in this study. But so far, praise a little bit clarified, I guess. Okay, so I'll have to move ahead for want of time. Now, having said this, that's that about the IUPAC nomenclature. Just review our earlier study, and with that you would be able to understand this better. The next thing we are going to get into under this particular aspect of the study is lab preparations. So how do we prepare your different halogens in the lab? Basically, if you want to prepare your different halogens in the lab, what are the different processes? Okay, we'll start with the first one. The very first one we are going to discuss is what we refer to as your alkane substitution reaction. So, well, yeah. So, number 1 is from alkanes. Let's use that. How can your halogens or halogeno compounds be prepared from alkanes? By halogenation. Halogenation is a substitution reaction. Halogenation of alkanes. So the implication is that you should first understand that when you talk about alkanes, they are hydrocarbons that possess only single bonds, and there are 2 major reactions they undergo. Number 1 is combustion reaction. If it occurs completely, it is only going to give carbon 4 oxide and water. The second one is substitution. And the most important substitution reaction that occurs in alkanes is halogenation reaction. How does it occur? First of all, is substitution reaction generally describes a replacement reaction. Yes, we are still going to talk about that, but let me just put it out now that whenever you talk about substitution reaction, let's look at the proper definition to that. So what's a substitution reaction? A substitution reaction is also known as a single displacement reaction or a single substitution reaction. Is a chemical reaction during which one functional group in a chemical compound is replaced by another functional group. So basically, the emphasis in substitution reaction is the term replacement. So I want you to just have that in mind, that anytime you think about substitution reaction, think about replacement. Now, there are so many forms of substitution reaction. The major forms are your nucleophilic substitution and your electrophilic substitution. We are going to discuss those ones later. The one we are going to consider now is what we refer to as your radical substitution, which occurs in alkanes. How does it occur? Imagine you have, for instance, we are going to use methane. Remember that methane has, if you remember, methane is one carbon attached to 4 different hydrogen atoms, basically. Sorry, just trying to get, let me use a different color, a brighter color. Okay, so where you have one carbon attached to 4 different hydrogens, this is 1, 2, 3, 4. And now, the first thing I would like you to note is that halogenation is a reaction in which you substitute a halogen for hydrogen in an alkane. And how does that occur? First thing that happens is that this particular halogen must first be split into 2. You know, halogens are diatomic in nature. If you do not know that, just know it now. That this halogen, when you write it as Cl2, is written like this. But what happens is that they actually divide, and when they break, one of them would go and attack a hydrogen atom. Please, it is important to note that substitution occurs one by one. You can't have these 2 chlorine atoms substituting 2 hydrogens. It doesn't work like that. It happens singly. That is, one chlorine will attack a hydrogen and substitute it before another chlorine goes. Now, when this chlorine attacks this hydrogen, it breaks this bond. And once it severs this bond, the implication is that you will now have that the hydrogen and the chlorine will combine together and form HCl. This is a different way, meaning that this particular guy will now be allowed to stay alone. So, you've broken the hydrogen. You now have that one end is now free. This end that is now free will now be attacked by the second chlorine. And once it is attacked by the second chlorine, it now leads to the production of C, hydrogen here, hydrogen here, hydrogen here, and then instead of another hydrogen here, you have chlorine instead. So which means that the end of this whole reaction is that a monochloroalkane is produced initially plus HCl. So that's that about substitution. One of the chlorine ion breaks the bond between hydrogen and replaces it. And once it replaces it, it occurs one by one. This hydrogen that are left will now combine with that chlorine that attacked it and go away. While the second chlorine will now go and attach itself here. And this is what we refer to as substitution reaction. So which means if you are given a question and they ask you halogenation of methane gives what product? What gas is given off after halogenation of any alkane? The gas that is usually produced, or once they ask you that question, or what halo, you find out that first of all you are going to have a haloalkane produced, and then you must have a halo halide gas produced, or a hydrogen halide gas produced. Basically, I take it again that in this reaction, one of the chlorine atoms will attack the hydrogen, sever this bond, and collect it. The 2 of them will now form hydrogen chloride, while the second chlorine will now attack that space that is remaining and replace it. Once it fills that space, it means that you now have 2 products. One of them is a monohaloalkane, while the second one is the hydrogen halide in this case. Okay, any confusion so far? Any confusion based on what I explained? Any confusion based on what I explained? Yeah. Any confusion based on what I explained? I need your response for me to be able to continue. If you have a confusing part, I'll just briefly talk about it and move ahead. Okay, so that's that. Praise, are you still here? Any confusion from Praise? Okay, now let's move ahead basically. Now, I haven't said this. So back to the first thing. I said the first reaction is the production of your haloalkane from alkanes, and I said it occurs by substitution. Now let's consider this reaction. Now remember, if you have CH4 and it reacts with Cl2, based on what I explained, one of the chlorines will replace a hydrogen, so it becomes CH3Cl, and then you have HCl. Now if you further react this CH3Cl with another chlorine, what happens? The same process occurs. It will split, replace one hydrogen, so it will now be CH2 and then Cl2, and then remember HCl has to be formed. You now take this particular guy and react it again with another chlorine. Automatically what happens is one of the chlorine replaces one hydrogen, the hydrogen attacks the other one, and they form HCl. So you have plus HCl, and then you have CHCl3 and HCl basically. Then finally, if you now take this CHCl3 and then react it with another sorry, not HCl, react it with another chlorine molecule, you are now going to have Cl4 plus H plus HCl, and you have that basically. So this is how the reaction occurs. Now, points to note: halogenation reaction occurs in the presence of sunlight or UV rays. Catalyst for this reaction, is the sunlight or UV rays. The implication is that if there are no sunlight or UV rays, the reaction is most likely not going to occur. It will not be able to attain the activated complex or absorb enough activation energy for it to be able to convert or perform the substitution reaction. So I presume this is clear, and that is basically the process involved in producing alkanes, basically. Sorry, haloalkane. Remember, we are dealing with the lab preparation of haloalkanes or halogeno organic compounds, and I said the first one is from alkanes. How do we get to produce them from alkanes? By substitution reaction, and the substitution reaction is what we refer to as halogenation. In this case, I said that the catalyst for this reaction is sunlight or UV rays. This is a very important point to note. Okay, now with that said, the next one we are going to get into is from alkynes and alkenes. And if you are going to produce a halo organic compound from alkynes and alkenes, it is done by an addition reaction. Now, there are two major addition reactions. Okay, now let me just say something about addition reaction. When you are dealing with your substitution reaction, it basically deals with organic compounds that possess only single bonds. The implication is that atoms completely surround, the four atoms that are supposed to be bonded to carbon completely surround that particular carbon atom. So it is referred to as a saturated compound. So saturated compounds preferably undergo substitution because they are filled. A very good illustration is, imagine for instance you have a competition between two teams, and one of the team has 10 players, the other has 11, and the match started. The team with 11 players, which is complete, when another player for that team comes, will there be a substitution or an addition to that team that is already 11? Yes, that's a question put out to you guys. You have a team of 10 and 11, and they are playing football. Originally it should be 11 and 11 as we know, but you have 10 and 11. And then let's say we have team, okay, let me use team yellow. Team yellow has 11 players. Oh, my brush size, sorry. Let me just correct something quickly. Okay, so team yellow has 11 players and team white has 10 players. Now imagine that someone from team yellow suddenly decides to join. One player comes. Are you going to add or are you going to substitute? Because this is food, are you going to do addition or substitution? So please let me have your answers. Addition or substitution? Will you have to perform an addition reaction when it is a full team? In team yellow, will you have addition reaction or substitution, though it's complete? So yes, let me have your answers quickly. Yeah, I'm still waiting for our answers. Okay. Full team substitution, exactly. So once you have that, yeah, that's and Kachi's answer is correct. Once you have that, it is filled. It is filled. You only can undergo substitution. That is why we said saturated compounds. Saturated compounds can only go through substitution. It is not possible to have addition for a saturated compound. So if you haven't taken note of this before, please take note of this. Saturated compounds undergo substitution reactions. They cannot undergo addition reactions. So just have that in mind. That saturated compounds undergo substitution reaction, they cannot undergo addition reaction. For any reason, there is no reason to perform an addition reaction in a saturated compound. And what do I mean by a saturated compound? A compound where there are only single bonds between carbon atoms. Just have that in mind. A saturated compound, how do you know that a compound is saturated? Once you notice that there are only single bonds between carbon atoms, it is saturated. So just have that in mind. Okay, now we come to this guy. Team White has 10 players. For Team White, there are 10 players. If another player from Team White joins the team, another player from Team White joins the team. Sorry, my pen is acting up a little bit. I want to correct that. Okay, so imagine somebody from Team White, just one person, joins the team and wants to play. Please, are you going to add to that team or substitute? Yes, just one answer and I continue. Okay, so for Team White, as Kachi said, you are simply going to do an addition reaction. So just have that in mind. Now, with all these illustrations I just made, it's very basic. It's very basic. I'll come back to this. But the basic principle you need to take note of is, once you have saturated, a saturated compound can only undergo substitution reaction. But if, for instance, it is unsaturated, the preferable thing to do is addition, basically. Now, there are conditions where an unsaturated compound tends to exhibit or undergo substitution reaction. We are going to discuss that later on. You get, just have that in mind, that terminal alkynes are unsaturated. You get, I said saturated, another term unsaturated, only single bonds. Only single bonds between carbon. Then unsaturated, multiple bonds. When I say multiple, I mean double or triple. Multiple bonds between carbon. So once you see an organic compound and they tell you it's an ene or ine, once you see ene or ine, just know that the reaction that it can undergo is addition. But once it is an ane, meaning that it has single bonds, automatically it is substitution reaction, basically. Now, but I said something that there is like a situation where an unsaturated compound can undergo substitution, and I said the only unsaturated compounds that undergo substitution reaction are your terminal alkynes and then your aromatic compounds. We'll get to discuss that as we go further. So just have that in mind, that there is a possibility that unsaturated can undergo substitution, but there is no possibility that saturated can undergo addition. You get what I'm saying? So conditions where unsaturated undergoes, so terminal alkynes can undergo substitution. Another group of compounds that can undergo substitution are your aromatics. Your aromatics can also undergo substitution. However, every other unsaturated compound is supposed to undergo addition. The only exception is terminal alkynes and aromatics. So just have that in mind. Okay, so but generally speaking, once it is saturated, you think about substitution. And you know, it's actually common sense. You know, Team Yellow had 11 players. The only thing you can do about these 11 players is to substitute, remove one and put one back, replace. But Team White can decide that they will remove one, put one, which is substitution, or they can decide to add, which means in Team White you can either have an addition reaction, addition or substitution. But then I told you that there are specific conditions before you don't go substitution. The major reaction that happens in unsaturated or the preferred one is addition. However, there are conditions where you could have substitution. Take for instance now, maybe one of the players, they play handball, you come out and put this other guy instead of, let's leave that and continue basically. But my point is this: saturated substitution, unsaturated addition. Okay, let's move ahead. Now we come back to what we are saying. We are discussing lab preparation of halogeno compounds, and we said from alkanes and alkynes. Please note that alkenes and alkynes are unsaturated, which implies that the only reaction that they can undergo is by addition reaction. Okay, so there are two major addition reactions that occurs to produce your haloalkanes from alkenes and alkynes. The very first one I would like to talk about is what we refer to as your hydrohalogenation. Halogenation reaction. Okay, so when you say hydrohalogenation, it means that you are adding, this involves addition of a hydrogen halide. Examples of your hydrogen halides: hydrogen chloride, hydrogen fluoride, hydrogen bromide, hydrogen iodide. So once you are adding a hydrogen halide, the type of reaction you are undergoing or putting that through is hydrohalogenation. Okay, before I continue, I would like to let me quickly set up something just in 1 minute basically. Class today, I just want to put up a slide. You get, let me just put up this slide so that everybody would flow basically. I just want to put up a slide quickly, so the class is still going on. Maybe I just, yes, yeah, let me just put up a slide quickly. I'm setting that up. It would where is it? Okay, Markovnikov's Zaystev's. Okay, Control C. Where is it? CHEM122, Control V. Where is it? Okay. Should be done in a jiffy. Markovnikov's. I just want to put it out so that everybody can see it basically, because we are going to be applying that principle now. Okay, now it's launch CHEM122. Markovnikov's. Where is the slide for Markovnikov's? Okay, yeah, we are live. Okay, I think that's that. Yeah, sorry about that. Now, before we continue, so I said the first addition reaction we're going to consider for the production of a haloalkane is hydrohalogenation reaction. Now, hydrohalogenation reaction implies that you are going to be adding a hydrogen halide. The general principle in addition reaction is this: imagine you have, let's say you have this guy now. This is 18. And you want to add HBr. What basically happens in addition is that this bond will now be severed or broken, and then H will now collect one side of the bond, while Br will collect the other side of the bond, which means you're now going to have C, H is here originally now, and then C, H was here originally. That bond that was broken will now be shared. One will be here, one will be here. H will collect one, then Br will collect one. And that's that basically about that. So just have that in mind, that this is what we refer to as your hydrohalogenation reaction. Now, but before you would be able to know where H will go and where Br will go, you need to understand the principle known as Markovnikov's rule. Because will H go to the first one, or will H go to the second one, or will Br go to the first one, or will Br go to the second one? All these things are simply dependent on the principle stated by Markovnikov's. And what is Markovnikov's rule trying to say? Let me put it out on the screen so that everybody can see it. Now, Markovnikov's rule states that when a heteroatomic molecule containing hydrogen attacks a carbon-carbon multiple bond during an addition reaction, the hydrogen atom attacks the carbon atom of the double bond with more hydrogen. So I'm going to explain this basically, but you can put this down quickly. Just take 30 seconds and put this down quickly. Markovnikov's rule, what it states. So take 30 seconds, put this down quickly. Basically, I presume we are done, so I can remove it. Yeah. Okay, so I'm going to have to take it out of the screen, basically. Okay, so we can use the board. Now, what is Markovnikov's rule simply trying to say? What it's trying to say is that anytime you have a hydrohalogenation reaction, a reaction between an unsaturated compound, let's use this compound. Take for instance now, we have propene. I'm going to intentionally use propene. Remember, I told you guys that in the structure, carbon, after putting your carbon and double bond, the remaining bonds will be filled with, space will be filled with hydrogen, where carbon has 4 bonds. So 1, 2, 3, 4 is filled. Here is 1, 2, 3, 4. Carbon. There's no other hydrogen that will be added here, but here is CH3. Now, if you're adding HBr, for instance, if you want to perform this reaction, basically, will H attack, this is carbon number 1, carbon number 2, carbon number 3. Will H attack carbon number 1, or will H attack carbon number 2? That's the question that Markovnikov answered. Now, Markovnikov's rule simply states that in a situation where a molecule that has hydrogen is performing an addition reaction with an unsaturated compound, the hydrogen will attack the carbon double bond, which has higher number of hydrogen atoms. This carbon has 2 hydrogen atoms. This carbon has 1 hydrogen atom. Therefore, hydrogen will preferably attack this carbon, which has more hydrogen atom, while the non-hydrogen atom will attack the other carbon with less hydrogen atoms. So just have that in mind, that according to Markovnikov's rule, once you have hydrogen as one of the things that are going to attack the double bond, hydrogen will attack the carbon atom that has more hydrogen atoms. Hence, the major product of this reaction is going to be C. Let's put our single bond. We've broken the double bond. You get. So that one of the double bond, side of double that was broken, will have to go to hydrogen. This hydrogen. Because originally there were hydrogen here. And then the second one, hydrogen was initially here, will now go to Br. Why? The non-hydrogen atom or molecule will attack the carbon with less hydrogen, while the hydrogen will attack the carbon with more hydrogen. That's basically how addition reaction occurs. And this is what we refer to as Markovnikov's rule. This particular thing is used to determine major products of reactions. Now, before I move ahead, I would like to ask, is there any confusion so far? Is there any confusion so far? Any confusion so far or question? Is there any confusion or question so far? Quickly indicate. Is there any question or confusion so far? Quickly indicate so we can move ahead. So I'm not there again. No. Okay, from Kachi, none. The other guy, the other students in the class, yes. Okay, I will have to just continue. Okay, let me just give you guys this question. You guys should try it. Now, imagine I have a hydrohalogenation reaction. According to Markovnikov's rule, I would like you to give me the major product of this reaction. Okay, you name it too. Imagine, for instance, you had something like this. Okay, and then you had hydrogen there, hydrogen there, hydrogen there. 1, 2, 1, 2, 3. And then this is HCl. So can you give me the name of the major product? Just the name. You don't have to show me the structure. Just tell me the name of the major product of this reaction. Because that's basically what happens. What is the name of the major product of this reaction? When this but 1 is reacting with hydrogen chloride. Okay, so quickly do that. I'm expecting your answer. Okay. Do we have any answer yet? 2-chlorobutane. Yeah, that's the answer basically. Yeah, correct. Basically. Because, okay, so let's show how it is 2-chlorobutane. So that's that going. So what's this going to happen? What's going to happen here is basically hydrogen here will have to attack this guy, while chlorine will have to attack this guy, which means when they break the bond, chlorine go there, hydrogen go there, fill it up with the remaining parts, and you have that this is going to be according to what we have, this is going to be 2-chlorobutane. So that is that about Markovnikov's rule, basically. So, as I said, Markovnikov's rule states that, let me put that up again, so that we can all see that and then move on to the next one. So it basically states that when a heteroatomic molecule containing hydrogen attacks a carbon-carbon multiple bond during an addition reaction, the hydrogen atom attacks the carbon of the double bond with more hydrogen atoms. Basically that. So let's move ahead. Now, there is another form of addition of halogen compounds, and that is what we refer to as radical addition. That is what we refer to as radical addition. That is what we refer to as radical addition. Now, radical addition is basically an anti-Markovnikov's addition. And what is the condition to perform radical addition? When the catalyst is hydrogen peroxide. So once you are performing a reaction, an addition reaction, like for instance, if we had something like this, hydrogen, 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 H3, and we have HCl, and you notice that the catalyst is H2O2, it means that you are not going to use Markovnikov's rule. You will do the opposite, which means H will go to where hydrogen is less, and chlorine will go to where hydrogen is more. And what you are going to have at this point is going to be Cl to the first carbon, hydrogen to the second carbon, H3, H, H, H. And you have that. This is what we refer to as radical addition. So in radical addition, it's basically an addition reaction that does not follow Markovnikov's rule. Markovnikov's rule states that the hydrogen should go to the carbon atom where there is more. That's Markovnikov's rule. But this is a radical addition because you notice that it's an addition process in which the catalyst is your hydrogen peroxide. So I'm just saying this for you to take note of that, basically. So if we are dealing with alkynes, okay, imagine you have this reaction. So give me the product of this reaction. Let's say you have this. You're dealing with alkynes. What is likely going to be the product of this reaction? What's going to be the likely product of this reaction? Okay, so you are going to name the compound produced after this particular reaction. Okay, so what's the name of the compound that will be produced after you perform this reaction? So do that quickly. Do that quickly. The name of the compound produced after this reaction. Quickly. Okay. What do we have? Yeah, any answer, just one answer and I continue. Okay, 2 bromo, 3 iodo, butan 2 oh, makes sense. But there's only one problem there. We are going to find out that problem. You get. So I would like you guys to go back and review our study on naming because it's going to help us. Now, as we know, hydrogen is going to attack this carbon. Sorry, this other carbon. According to Markovnikov's rule, hydrogen will attack this guy because it has more hydrogen atom, while iodine will attack the carbon multiple bond with less hydrogen atom. So let's get to that. The product is now going to be C. If it breaks, it just broke 1, which means we are going to have a double bond here. If I had written 2, it means 2 will attack, but I said 1, so it will break only 1. So we are going to have the initial hydrogen that was there, then hydrogen, we said hydrogen will attack this one, so which means we are going to have hydrogen here. Why? Markovnikov's rule states that when you have a heteroatomic molecule containing hydrogen, hydrogen attacks the carbon multiple bond, which already has more hydrogen than the other. Between these 2 carbon atoms of the multiple bond, hydrogen is 1 here, hydrogen is 0 here, which means hydrogen will go to the carbon that has more, which is this one, while the other atom or species will go to the carbon that has less, which is in case this one. So iodine will come to this place, and then we are now going to have C. There was Br here and OH on this place, and then CH3. If we are going to number, we're going to number like this: 1, 2, 3, 4. Now, in naming, the first thing you do is to indicate the major functional group, which in this case is alcohol, and then you also have alkene. So let's name this compound now. Before we name the compound, the parent's name is what we're going to start with. 4 carbon atoms is going to be but. But we notice a double bond. And where's the double bond between 3 and 4? So this is going to be but 3 in. Then we have an alcohol, which is all. Where is the all located on number 2? 2 all. And that's that basically. So with this said, we now go to the functional groups. The substituents. Bromine is on number 2. Iodine is on number 3. So this is going to be 2 bromo, 3 iodo, but 3 in 2 all. Hope this is clear. Yeah, Kachi. Hope it's clear. Okay. Let's do that quickly. I would like us to get into other reactions before it's time. Yes, yes, yes. Okay, makes sense. So let's move ahead. Yeah. Now. Okay. Okay. Now, having said that, we'll have to push on. Yes, it happens step by step. Yeah, yeah. What are you asking about? I guess you're asking about the naming process. So if you notice, yes, the addition reaction, you could say it happens step by step. My naming process, I had to look into it, took it one after each other, basically. I presume that's what you meant. Now let's continue. Now, that is that for your hydrohalogenation reaction. And I said that hydrohalogenation reaction follows Markovnikov's rule, which says that hydrogen will go to the carbon that has more hydrogen, and then the other guy will go to carbon that has less hydrogen, basically. And I've told you that you can have an anti-Markovnikov addition. That is when it is referred to as a radical addition. The catalyst used to make it a radical addition is hydrogen peroxide. Okay, so we've discussed that. So what we were discussing, remember, is producing halogeno from alkenes and alkynes. And one of the reasons I'm teaching these things is because once you understand the way this reaction occurs, if they want, let them twist the question upside down. You will just know the product and get your answer. So halogeno from alkenes and alkynes, and we said that it's produced from an addition reaction. And the extra thing we said is that the first reaction we considered is hydrohalogenation. Then the second one we considered is what we refer to as your halogenation reaction. As you know, halogenation means addition of an halogen. So if I have something like this, and I'm introducing a halogen. Halogen is chlorine, bromine, but then remember they are diatomic. So two of them in one molecule. So one of the chlorine attacks, there's no need for Markovnikov's rule, they are the same thing. So one takes one, the other one takes one. Basically, it will still be the same thing. So you're going to have in this case, okay. Okay, so let me ask a question. Is this a vicinal dihalide or a geminal dihalide? Yes, that's the question. Is this a vicinal dihalide? Based on what we discussed initially, is the product a vicinal dihalide or a geminal dihalide? We discussed this initially in the class, so put out your answers basically and do that quickly. Are you going to have this as a vicinal dihalide or a geminal dihalide? Put out your answers quickly. Vicinal. Exactly, it's vicinal. Why is it vicinal? Because it's adjacent, basically. Okay, makes sense. So let's move ahead. So the name of this compound is going to be 1,2-dichloroethane, and it is a vicinal dihalide. Why is it a vicinal dihalide? Because the two halogens are on adjacent carbon atoms. Okay, so that's basically about halogenation. Remember that for halogenation to occur, you have to use ultraviolet rays or sunlight, whether it is halogenation by addition or halogenation by substitution. You get, this is now an addition halogenation. What we discussed with respect to alkane was a substitution halogenation, basically, and that's that basically. Okay, now the third method of producing your halo organic compounds, we are going to now consider your aryl halides. How do you produce aryl halides? Now, aryl halides are basically produced when you react benzene. When you react benzene with your halogens, but there has to be a catalyst involved. Now, if I want to react benzene with something like bromine, and I want this reaction to be a substitution reaction and not an addition reaction, what I must do is to introduce the bromine is diatomic, so just take note of that. I am going to introduce the catalyst aluminium bromide. Another catalyst that can be used is iron 3 bromide. Now notice something. When I'm adding bromine, I will use aluminum bromide or iron bromide. So basic question is, what if I'm adding chlorine? What do you think will be the catalyst I will use? Oh yeah, answer. Yes, when I'm adding chlorine, what is going to be the likely catalyst I'm going to use? This is a discussion class, that's why I'm putting out questions. Yes, I said that I am adding bromine, substituting bromine, and I use aluminum bromide or iron 3 bromide. When I'm now adding chlorine, what is the likely catalyst I'm going to use? Okay, put out your answer, because these things are like very direct and easy to understand. Yes. Okay. I'm expecting an answer before I continue. One answer and I move ahead. Oh yeah, I'm gonna do time no day. Yes, one answer. It's common sense something, no. I said when I was adding bromine, substituting bromine, aluminum chloride, exactly. So that's that basically. Now, the only reason I will not involve iodine and fluorine is iodine and fluorine are they don't usually have direct reactions for most of these things. I will still explain why. Okay, the basic reason why, the basic reason for omitting iodine and fluorine in this reaction is this. Fluorine is very electronegative and the reaction is usually extremely exothermic or explosive. So we don't usually perform a direct substitution reaction of fluorine. You get, when you want to do this, you don't do that because it is highly explosive. In the case of iodine, the reactions with iodine are too slow because it is the least electronegative halide amongst them. So preferably when you have a direct substitution reaction, what you do is using bromine or chlorine. Those ones will go. Then after producing bromine or bromo or chloroalkanes, you now use them to produce your fluoro and your iodoalkanes. We'll discuss that in details, but I'm just saying this for now, that you should just have this in mind, that whenever you're adding a halogen directly, the ones that are preferably done are bromine and chlorine. And for the case of substitution of, this is an unsaturated compound, and I told you that the exception, this is a substitution reaction, aryl halides by substitution. If it was an addition process, you are going to have your cyclohaloalkanes basically, but this aryl halide means that there has to be a benzene ring. I know that when you are doing this, if bromine is to be substituted, before I even continue, know that this is a carbon and there is hydrogen here. There is hydrogen here. There is hydrogen here. There is hydrogen here. It's just that we are using the skeletal structure. Basically, that's why. So if you are to do this, what happens is Br will split now. Attack, collect bromine. Then the other bromine will now come here and replace this. And once you do this, you are now going to have that the product will now be, the hydrogen was replaced with bromine, and then the other bromine will now combine with that hydrogen that left and it becomes HBr. So this is your product. In this case, if I have a benzene ring and chlorine, basically what I'm going to have here is Cl attached to my benzene ring and then plus HCl. Remember, the catalyst in this case is either you use iron 3 bromide or you use aluminium, sorry, not bromide, it's chlorine we are adding. So iron 3 chloride or aluminium chloride. So basically that's that on how to form the aryl halides. So if you notice, what we've been doing so far is understanding the different reactions. Why we need to understand them is so that if these things are changed, you will know likely how to go about them. And that's that basically. Okay, so I would have to move ahead for want of time, but I hope this was clear. Students in class, hope this is clear. Hope what I explained so far is clear. Hope it's clear. Hope it's clear. One answer and I continue. There's no time. Hope it's clear. One answer and I continue. There's no time. Yes, I'm still waiting for an answer. Okay, I'm not getting any yet. Okay, yeah, good. So let's continue. Now, so that's that about the that form of production. So we've discussed 3 from alkanes by normal substitution. I told you that the emphasis of that reaction is catalyst. Catalyst there is UV rays in halogenation reaction. In alkenes, if you are going to perform a hydrohalogenation of alkene or alkyne, you must, or you are going to deal with the Markovnikov's rule. And then when you are dealing with aryl halides, halogenation is how to produce aryl halides by substitution. You get, but then take note of the catalyst. If it is bromine you are adding or substituting, sorry, you have to use aluminum bromide or iron 3 bromide. If it's chlorine, iron chloride or iron 3 chloride or aluminum chloride, basically. So that's that basically. Now, having said this, as I said, if you notice, products, catalysts, and reactants are what I have been analyzing or checking. So it's important you put those things to your head. Now, after discussing this, the very next procedure we are going to consider in the production of your haloalkanes are basically from your alcohols. Now, in production from your alcohols, the major thing you are going to be considering is that tertiary alcohols, secondary alcohols, and primary alcohols actually react differently to produce your haloalkanes. And the reaction basically occurs by combining your alcohol with your alcohol with your hydrogen halides, basically. I see what I mean by that. Okay, so imagine, for instance, you have ROH. This is an alcohol and it is reacting with HBr. What is actually going to happen here is that hydrogen and hydroxyl will combine and form water. Then this Br will replace this. So your reaction is going to be RO attached to Br plus H2O. Now, it's important that you note that for this reaction to occur, one of the major catalysts in this case is going to be a zinc salt of that particular ion. So you have ZnBr2 as the catalyst, basically. So once you're able to do this, you are likely going to have this particular product. Okay, which means that if, for instance, I want to perform this for my hydrogen iodide, it's now going to be Zni2. If this happens, I am going to have R attached to I plus H2O. So this is what we refer to as a more like a dehydrolysis reaction, where you are removing water. You get. So in this case, you will notice that bromine replaced the OH and OH had to leave, basically. In this case, it's still a substitution reaction. We are still going to discuss the form of substitution reaction later. So I take it again that when alcohols react with your hydrohalides, they can produce your haloalkanes. How do they produce that? Basically, the hydrogen will attack the OH and two of them will combine to form water. With bromine, then it means that you are going to be dealing with zinc bromide. If you are dealing with iodine, then you are going to be dealing with zinc iodide. Basically, this is the reaction required to produce from an alcohol. Now, what is very important for you to note is that this particular reaction can actually determine or is used to differentiate between your primary, your secondary, and your tertiary alkanols. Yes, the reaction between an alcohol and a hydrogen halide can actually differentiate a primary, secondary, and tertiary alcohol. So note this: the tertiary alcohols react faster. Tertiary alcohols react faster, or react the fastest. Let's use that. So they react the fastest with your hydrogen halides. Please take note of this. Put this down. Take note of this. Tertiary alcohols react fastest with hydrogen halides. The second fastest is the secondary alcohols. They react, or they are the second fastest. Let's use that. alcohols. So they are the second fastest with hydrogen halides. And then finally is your primary alcohols. They react slowest with hydrogen halides. Now, as I said, this particular procedure is what is used to differentiate tertiary alcohol. I'm not talking about your tertiary halides, your secondary halides and your primary halides. No, I'm talking about alcohols, and we discussed this earlier in the class, that when you consider the same principle applied in determining primary, secondary, and tertiary halides is the same thing applied in determining primary, secondary, and tertiary alcohols. However, it's not the same when you are dealing with your amine group. Your primary amine, your tertiary amine, your secondary amines, those ones, we'll discuss that differently. It's not the same principle that applies. But for your halides and your alcohols, once the OH or functional group is attached to the primary carbon, it becomes a primary alkanol. Attached to a secondary, it becomes a secondary alkanol. Attached to a tertiary, it becomes a tertiary. So if you want to differentiate between the three of them, you simply consider the reaction with a hydrogen halide. Now, the most popular hydrogen halide that is used to test or differentiate between alcohol is what we refer to as Lucas reagent. Please take note of this. Lucas reagent is a mixture of hydrogen chloride and zinc chloride. The zinc chloride is more like the catalyst that catalyzes the hydrohalogenation or the hydrolysis of alcohol. So, what happens in this case? I told you that tertiary is greater in reactivity than secondary, and secondary is greater in reactivity than primary. What basically happens with the Lucas reagent is that when you react a tertiary alcohol with Lucas reagent, the compound produced is actually turbid. You get it's unclear, it forms a colloidal, a suspension, basically mixture, and you would notice turbidity immediately. Turbidity means unclarity, so you will notice that the solution of the mixture becomes turbid immediately. Why? As I said, the reaction is the fastest with tertiary alcohol. Reaction of an alcohol with a hydrogen halide, let's use X to represent halide, fastest is tertiary, followed by secondary, followed by primary. So when you are looking at the degree or height of reactivity, the difference or how to differentiate between tertiary, secondary, and primary is using this reaction. You get. So with Lucas reagent, turbidity shows immediately. With with Lucas reagent, turbidity shows immediately for tertiary alcohols. For secondary alcohols, it shows after 5 minutes or thereabout. For secondary alcohols, turbidity shows after 5 minutes, which means the reaction occurs basically after 5 minutes. Secondary alcohols plus Lucas reagent, turbidity after 5 minutes. Now, for your primary alcohols plus Lucas reagent, we could say that turbidity doesn't eventually show. No turbidity. Now, why would we say no turbidity? Because the reaction occurs very, 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 very slow. So you could stay an hour plus and then it has not yet shown. So basically, you can use that to differentiate them. Tertiary alcohols react fastest with Lucas reagent. Secondary alcohols are the second fastest, so the turbidity shows after 5 minutes, while primary alcohols are the slowest. I hope this is clear, basically. Those of us still online, hope this is clear. What I explained about the alcohol, is it clear? Is it clear? Oh yeah, I'll talk. Let's continue. There's no time. I want to go ahead and get into other reactions, basically. Okay. Okay, very good. Now, the next lab preparation we're going to consider is the lab preparation that has to do with a reaction between a carbonyl group compound and nitrous acid. Okay, sorry, did I say carbonyl group? No, not carbonyl group this time around. An amine and your nitrous acid. An amine and your nitrous acid. Yeah, yeah. Okay. Now, as I was saying, in that particular process, we are going to be considering how an amine is going to produce what will eventually produce a halo organic compound, basically. And what happens there? First of all, is that you need to understand that there are classes of amines, basically, just as you have primary, secondary, and tertiary. In fact, let me just explain that quickly. Now, amines are produced from ammonia. Amines are produced from ammonia. And how are we going to classify primary, secondary, and tertiary amines? Unlike the primary, secondary, and tertiary haloalkanes and the primary, secondary, and tertiary alcohols, the arrangement for amines is simply based on how many hydrogen is replaced around ammonia. So let's get to work. Now, if for instance I have a reaction where an amine is reacting with a particular compound, and after it reacts only one hydrogen is replaced, and I have this. Once I replace only one hydrogen with an alkyl group, this is what we refer to as a primary amine. So when you have a scenario where only one hydrogen is replaced, which means that once you have a compound where nitrogen is attached to two hydrogens, automatically you know that this is a primary amine. We are still going to discuss amines later, but I'm just using this to highlight some points. That once you are dealing with an amine group, amine is derived by replacing hydrogen atoms in ammonia. That's basically how to produce amines, basically. So how do you know the primary? The primary amine is produced when you replace one hydrogen, which means if you replace one hydrogen with an alkyl group, you have a primary amine. And how do we get that? The important thing, I think what helps me basically, or what I do is, I consider the number of hydrogen atoms instead. Every primary amine has two hydrogen atoms, which means secondary would have one, and tertiary will have none. So basically, with this, you can easily identify the difference between the primary structural differences. It's not a reactional difference, so we're not considering reaction in this case. We're just looking at it based on structure. So as I said, a primary amine produces by replacing one hydrogen. So once I replace one hydrogen, primary, which means if I replace two hydrogen atoms with alkyl groups, what I'm going to produce in this case is a secondary. So this is primary. Why is this primary? Because only one hydrogen was replaced. Then secondary is when two, which means if I'm dealing with a tertiary, it's very obvious. When I replace the three of them, it becomes tertiary. So R, R, and R, and this is what we refer to as tertiary amines. This is secondary amine, and then in this case, this is a primary amine. Why is this a primary amine? Basically because one was replaced, primary. If two hydrogens is replaced, secondary. If three is replaced around nitrogen, it becomes tertiary. And that's that basically. So yes, I hope this is clear. Hope no confusion. We are going to discuss amines later. You get. So don't worry about this, but I just wanted to highlight this because of the reaction we're about to talk about. Hope is clear. Mona they respond quickly. Time no day. Oh yeah. Hope is clear. Primary, secondary, tertiary, clarified. Okay, very good. So yeah, just one answer is what I need from one person. The rest of you, yeah, if you have questions, you could ask later. Okay, now I haven't mentioned this. One of the things that I use to differentiate, what we discussed now is just the structural differences between primary, secondary, and tertiary amines. What we're going to talk about now is a reagent that is used to differentiate primary, secondary, and tertiary based on the type of products they give. You know, we use Lucas reagents and differentiated primary, secondary, and tertiary alcohols based on the reactions. We notice that tertiary reacts faster than secondary, and secondary reacts faster than primary. And please, this reaction is between alcohol and a hydrogen halide. You get, remember I told you what the catalyst is. But for Lucas reagent, specifically for Lucas reagent, the hydrogen halide involved is hydrogen chloride, you get, and the catalyst is zinc chloride. So just have that in mind basically, which means if I was dealing with hydrogen bromide, the catalyst would be zinc bromide. This is like quite basic if you are able to just take note of these headlines or points. Remember, when we are dealing with our aryl halides, I told you that if you are doing the halogenation of bromine, you're going to use aluminium bromide or iron 3 bromide. These are just basic. Once you understand these concepts, these reactions become very easy for you. Okay, so back to what we are doing. This is going to be the final lab preparation, and then we get into other things. What is that? What was I talking about? Now, the final lab preparation is actually from amines, you get, specifically primary amines. Primary amines. We could use any primary amine. We could use anyone. Let's say we have NH2, and I have obviously 2 hydrogen atoms will be here, 1 here and 1 here. Now, as I said, the particular reagent that is used to differentiate primary, secondary, and tertiary amines, one of them, there are many of them. There's the Hinsberg reagent, there's the but we are discussing this one in this case. We'll discuss the rest of them when we're talking about amines. What we are talking about here is nitrous acid. Nitrous acid is dioxynitrate 3 acid, nitrous acid. Okay, let me just put that down here. Okay, so as I said, how am I going to use nitrous acid to differentiate a primary, a secondary, and a tertiary amine? If you react nitrous acid with a primary amine, eventually the final product, you're going to have a colorless gas given out, depending on the condition. If it's primary, colorless gas will be given out. If it's secondary, you have nitroso, a nitroso amine given out. And then in the case of tertiary, you practically have no visible reaction. There would be a reaction, but it will not be visible, you get. As I said, this is not amine. We're going to discuss that later. But why I'm bringing this up now is because it's just to help us understand how these reactions will lead to the production of an alkane. Now, during this reaction, one of the major things that happens if it is a primary amine is that it leads to the production of what we call a diazonium compound. A diazonium compound is characterized by a triple bond between 2 nitrogen atoms, which is further attached to a carbon atom. Once you have this situation now, this is what we refer to as a diazonium. Once nitrogen, triple bond, and then another bond is now formed, joined with carbon, what you have is a diazonium substance. Now, in most cases, the diazonium ion is positive, you get. So, once it is positive, you can refer to it as a diazonium cation. So, I take it again, how do we form this diazonium cation? By having a nitrogen triple bond, and then you have an extra bond attached to carbon. Automatically, we are still going to discuss some things about bonding, which will help us understand the steric effect and inductive effect that made this to be positive. But just have that in mind that when an amine reacts with nitrous acid, it first produces an unstable diazonium state. And you have that this is the diazonium state. So imagine, okay, this is CH3C, which means we are going to have CH3C attached to nitrogen. Now, the 2 hydrogen atoms here will leave, and then this nitrogen from the nitrous acid will now come here, and then it's going to be N triple bond. Now, remember I told you that it is usually positive, so we'll give it a positive sign. So this is what we refer to as your diazonium cation. You get. Now, with this said, if you further react it with something like, let's say you have your NaCl, for instance, if you react it with your NaCl or any other reagent, or just introduce a chlorine ion, anything that will just introduce a chlorine ion, it could be an acid, it could be anything. In most cases, yeah, an acid could work, you get, because it will help catalyze the reaction. So you use hydrochloric acid just to introduce chlorine ion. Automatically, this chlorine ion will replace this diazonium, and then you are now going to have CH3, CH2, and then Cl. Now, once the diazonium comes out, it will come out as nitrogen gas, And that's that basically. So note, the diazonium cation is unstable. Is unstable. You get. So because it's unstable, it means that it will eventually have to react with something and then give products, basically. So I take it again. If an amine reacts with a nitrous acid, it would first give a diazonium cation. And I told you the diazonium is when nitrogen forms triple bond with nitrogen and is attached to a carbon atom in an organic chain. That's what we refer to as a diazonium complex or a diazonium compound. Remember, the diazonium end is actually a cation. You get. If you now attach an anion, in the case of chlorine, it replaces this nitrogen, and then you have this particular substance produced, basically. So that's that basically about the diazonium. Is there any question so far based on this? It's to some people it might be confusing, but I hope it's clear. Yes, those who still day class, hope it's clear. Yes, hope this is clear. Okay, very good, very good. Okay, if that's clear, the implication is that if I give you this reaction, you can actually do something with that for me. Imagine, okay, let's consider this for instance. Let's see. I would like you in your notes to probably write this down and give me the likely product of reacting. This is, if you remember, we said this is aniline, I meant to say. You get, if you remember in our initial study, aniline, where amine is combined with a benzene ring. If I react aniline with, and let me just, my nitrous acid, can you give me the likely product of this reaction? I would like you to write down the stepwise reactions and then tell me the answer to your final product in the reaction. You get, put down the stepwise reactions to get your final answer. You get, and then send it to the class group. I'll review that later, but just tell me your final answer in the comment section on the chat, the live chat basically. Okay, so do that quickly. We are supposed to be rounding off. Oh yeah, oh, sharp. I'm waiting for your answer. Oh. Waiting for your answer. And I see chlorobenzene. Yeah, makes sense. That's the answer. Chlorobenzene is produced basically, and you find out that the stepwise process is, first of all, let's do the reaction ourselves. First of all, hydrogen is replaced with nitrogen to form a diazonium complex. So N, you now have triple bond N, but this is going to be a diazonium complex. Diazonium cation. And then moving ahead, so this is going to be phenyl diazonium. That's basically how to name it. This is phenyl diazonium. You get, if we have chlorine, if you have bromine too, it could produce bromine. You get, then this chlorine replaces this. You now have this guy, Cl, that's chlorobenzene plus nitrogen gas. So that's why. So now this is actually a test for primary, tertiary, secondary and tertiary amines basically. You get, this is how to differentiate, test to differentiate, tests to differentiate. So just start taking note of this, that a reaction with nitrous acid is a test to differentiate primary, secondary and tertiary. How? When you react a primary amine with a nitrous acid, you are eventually going to have nitrogen gas produced. You get, because the diazonium complex is unstable. I told you it's unstable, which means it will give out these like two nitrogen atoms as a gas, and then you have a replacement and so on and so forth. So we're going to discuss this probably later in the study. But for now, this is a test. If it is primary, nitrogen gas is produced. If it is secondary, a yellow substance known as the nitroso amine will be produced. But if it is tertiary, no visible reaction. It's not that there will be no reaction, but the reaction is not visible. You will not see any change based on what is happening in your test tube or whatever thing you're using for the reaction. So that is that for the processes involved. So if we're going to run them down, the lab preparations of haloalkanes, number one is your from alkanes. And what do we get from alkanes? Halogenation, substitution. We said that the catalyst is UV rays. If you are dealing with alkenes and alkynes, we said that the reaction is going to be addition. We now further explain that if you are dealing with your hydrohalogenation, it has to follow Markov-Nikov's rule. But if you are dealing with your normal halogenation, you don't necessarily need to follow this rule. Just make sure you have your UV rays present. Okay, moving ahead, we kind of said one or two things about the Markov-Nikov's rule. We now talked about the anti-Markov-Nikov's rule, where we said that happens. Anti-Markov-Nikov's rule is known as your radical addition. And the catalyst for that process is H2O2. I'm just trying to reiterate some of the things we did. And that's that basically. Okay, then we went into producing from your, I think it was your alcohols. From your alcohols by reacting them with, let's use HX to represent the hydrogen halides. And I told you that the catalyst is a zinc halide, basically. Once you do this, you're going to produce water, H2O, and an RX, basically. And that's how it works. Okay, then we now went to producing your, from benzene. So from benzene, if you are reacting X, the catalyst has to be ALX3 or FeX3. I'm giving you general equations. So once you do that, you produce your X plus HBr, and this is what we refer to as your aryl halides. Okay, I think finally we now mentioned the amine production. Now please note, the amine that is used is a primary amine. If a primary amine is to react with nitrous acid, it's going to give diazonium complex. You get? Okay, so imagine, let's take this. Let's take this back. So primary amine is what is used, though. Have that in mind. That what is used in the production, the amine that is used in production of haloalkanes are your primary amine. So imagine you have, for instance, your arrow attached to NH2, and then you have it reacting with your nitrous acid. Basically, the product of that reaction is going to be arrow attached to N, triple bond N, which in this case is unstable. So this is a diazonium. Further reacting it with something, any electrophile. If you introduce an electrophile, it breaks it down further, and then you could have. Now, in this case, the electrophile, sorry, the nucleophile, I meant to say, introduce a nucleophile, not an electrophile. The nucleophile, in this case, has to be a halogen. So, let me just introduce X. So, which means if you do this reaction, you're going to have RX plus nitrogen gas produced, basically. So that's that basically about this whole process. And these are the 5 major ways of producing your halogens, halogeno organic compounds, basically. Okay, now we are done with the different lab preparations, and for want of time, we are going to get into the next one, which is the chemical properties. Chemical properties. Now, halogeno organic compounds undergo two major reactions. There could be multiple reactions occurring, but the major reactions they undergo are just two. Number one is elimination reaction, and number two is substitution reaction. Under substitution, you have your nucleophilic substitution and your electrophilic substitution. Electrophilic substitution. I now mentioned something that your aryl halides preferably go through your electrophilic substitution, while your aliphatic halides go through your nucleophilic substitution. Now, the extra thing I would like to put here is that under nucleophilic, there are two forms of nucleophilic substitution, which is the SN2 mechanism and the SN1 mechanism. We're going to discuss all these things, but I'm just trying to outline the major reactions. So just have that in mind, that these are the major reactions that occurs in your halo halide. I would like it if you put this down. If you are writing, put this down in this order. It would actually make, it's kind of summarized though. So put it down in this order, basically. Quickly do that in 2 minutes. In 1 minute, so that we can move ahead. Do that in 1 minute so we can move ahead. Okay, so I presume you are done with that. I am going to have to start from the elimination reaction. Okay, we might not be able to, for want of time, we might not be able to finish up everything, but we're going to definitely try to finish off elimination reaction. I think we are going to stop there for today because I have another class basically. So we are going to have to round up at elimination reaction and continue it up. If we still have time, we're going to, it's almost 9:30, I just noticed. But let's just start. Now, elimination reaction is the opposite of addition reaction. Elimination is the opposite of addition reaction. What do I mean by that? So let's look this up. Anytime you hear the term addition, addition leads to the removal of a multiple bond. Elimination leads to the formation of a multiple bond. I take it again. Addition leads to elimination of, addition reaction leads to removal of multiple bond. Elimination reaction leads to formation of multiple bond. So that's that basically. Now, in elimination reaction, what basically happens is this. If you are able to remove species, adjacent species, or species from adjacent carbon atoms, once you are able to remove species from adjacent carbon atoms, automatically it would give you the ability to perform elimination reactions. I take it again. Once you are able to remove species from adjacent carbon atoms. Okay, let's look at this. Imagine you have a particular reaction like this. and I remove, this is hydrogen, okay, no, this is fluorine, and this is hydrogen. If I remove hydrogen from here, let me use a different color, and remove fluorine from an adjacent carbon atom, the implication is this: it will lead to the production of something like this: hydrogen, 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 hydrogen. Notice that this place is now empty. What this will eventually lead to is that these two bonds will now link up, and once they link up, you are going to have a double bond. Okay, so we can decide to take note of this, that elimination is simply the opposite of addition. So when they say what's an elimination reaction, an elimination reaction is a reaction which involves the removal of species from adjacent carbon atoms to improve or increase unsaturation. I take it again. I don't have the slide basically, but just put that down. Elimination reaction is a reaction which involves the removal of species from adjacent carbon atoms to increase unsaturation of the compound. So if we are asked to compare and contrast, addition reaction leads to the removal of multiple bonds, elimination reaction leads to the formation of multiple bonds. Another contrast is that addition reaction increases saturation, elimination reaction increases unsaturation. So you can be putting these things down basically. So I hope this is understood. Hope it's clear. So far, hope it's clear. If I will be teaching something that is not clear, hope it's clear. Hope you get. Okay. Makes sense. Okay, no worries. Makes sense. So just have that in mind, that elimination is the opposite of addition. Where addition, whenever you do addition, you are increasing saturation. But whenever you do elimination, you are increasing unsaturation. Unsaturation is multiple bond now. So it means elimination reaction will lead to the formation of multiple bond. Now, the extra thing you are going to put down is that the catalyst for the reaction during elimination is an alcohol solution of sodium hydroxide or potassium hydroxide. So put that down. Catalyst for elimination reaction is an alcohol solution of sodium hydroxide. So basically a mixture of KOH and an alcohol. So you have that this is the catalyst for elimination. So this or this, alcohol. So, oh no, that's the wrong spelling of alcohol. What was I spelling? So just have that in mind, that in elimination reaction, the catalyst for elimination reaction is this or this, basically. And elimination means removing adjacent species to form a multiple bond. Okay, so let's consider elimination reaction. Now, there is a principle that controls every elimination reaction that occurs, and that principle was stated by Zeistev. That is what we refer to as Zeistev's rule. I'm going to put it out on the screen so that you can see that. I presume I have the slide here. Okay, so that's what we refer to as Zeistev's rule. Now, what is Zeistev's rule? Zeistev's rule simply states that during an elimination reaction, the major product is that product which has more substituents around the multiple bond. Okay, yeah, surrounding the multiple, not the same thing. I take it again. Zeistev's rule states that during an elimination reaction, the major product is that which has more substituents surrounding the multiple bond. So as I said, in elimination, you are basically removing. There's no complexity to that. But how are you going to remove? You have to remove according to Zeistev's rule. So let's see what Zeistev is trying to say. Now, imagine for instance I have a reaction, and during that reaction I am going to be reacting. Let's say I have C. Let's say I have C. Now, note that we are considering elimination reaction of a halo alkene or a halo organic compound. So imagine you have an elimination of, let's say, fluorine, hydrogen, 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 hydrogen. And I want to perform an elimination reaction. Remember, the catalyst is KOH in an alcohol solution. Okay, so let's perform it. Now, this is a halogen. And if I want to remove a halogen, I'll remove a halogen and an adjacent carbon hydrogen atom, or hydrogen from an adjacent carbon. So I can remove this halogen, fluorine, and remove this hydrogen. Sorry, let me address, my brush size was just changing. Okay, so I can remove this hydrogen, or I could decide to remove this particular halogen and remove this hydrogen. So you notice that in this case I have two options. Which one are you going to perform? Zaystev's rule will help you know that. Now, Zaystev's rule simply says that once you remove them, you check the number of substituents. You remove it such that you have more substituents surrounding the multiple bond. Okay, I think I need to take this off and then start that afresh to avoid confusion. So I take it again. Imagine, for instance, you have this compound and we want to perform an elimination reaction. Elimination means remove something, and in the case of most compounds, you are removing a species from adjacent carbon atoms. Hydrogen, chlorine, hydrogen, 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 hydrogen. Now, if we're going to eliminate, you eliminate two adjacent species. Now, we can either remove hydrogen here and chlorine here and have the multiple bond formed here, or we can remove chlorine here and halogen here, hydrogen here, because they are both adjacent, and have the multiple bond formed here. So the question is, which one of these two will now be the major product? Okay, let's form the first product. The first product that we're going to have, remember, the catalyst is KOH in an alcohol solution. Now, how do we form the first catalyst? First catalyst is the one with the white bond. So how do we get that? We have C, H, H, C. Now remember that when you remove here and here, this bond will now be free and they will join and form a double bond, C, C. Okay, which means that this is going to be hydrogen, H2 and H3. This is the first product. But this is not the major. We will understand which one is the major product. Now, or you are going to have between here and here. So let's write that between there and there. If you are going to have between these two, it means that you are going to have CH3 is still complete, C, C. So if you remove here and here, it means that the double bond is formed between the second and the third carbon. Okay, and then we have hydrogen, and then we have our CH3. Now the question is, which one of these two is the major product? According to Zaystev's rule, the first thing you need to do is to circle out your double bond. Circle out the multiple bond you can notice. So this is where the multiple bond is. If you circle it out, you notice that you only have one thing attached to it. Yes, you only have one alkyl group attached to it. But in the case when you circle this one out, you have an alkyl group attached to this side and another alkyl group attached to this side. According to Zaystev's rule, the implication is that the major product will have more things surrounding it. Let's look at that rule again. Let me put it out on the screen just in case you missed it. So it states that during an elimination reaction, the major product is that which has more substituents surrounding the multiple bond. So if we are to consider the two products we had, the first product we had only had one. That's if this is the multiple bond, carbon of the multiple bond, you only have one thing attached to on this side. But when you have this as the carbon of the multiple bond, you have an alkyl group here, another alkyl group here, which makes this to be the major product. And what is going to be our major product? This is the major product. This is the major product. Sorry, excuse me. I need to take Okay, so so far hope is clear. Hope is understood. Yes, your response, I need to know how far so I can know if to continue or re-explain. Okay, makes sense. Oh yeah, the implication is that, okay, let's name the compound. Okay, so this is the major, this is the minor. So if we are naming this compound, this is going to be boot 2 in, and this is boot in or boot 1 in. So you have that this is the minor, this is the major. Okay, I would like you to tell me the major product in this elimination reaction. Remember, follow the steps which states that the major product after an elimination reaction is the one which has more substituents surrounding the carbon-carbon multiple bond. Okay, so imagine I have this, for instance. Take for instance I have this compound. Okay. Yeah. So chlorine and hydrogen, and then I have OH here. Now please note, if the catalyst is potassium hydroxide in alcohol, it means that you are going to remove a hydrohalide. You get, there are scenarios where you remove water, that's H and OH, but that is when you have sulfuric acid. So please do not miss. In this case, what we are removing is a hydrohalide. You get, once you see potassium hydroxide and alcohol, you are removing a hydrohalide. I'm just saying this so that you'll be able to take note of that. So yes, can you tell us the major product in this particular reaction? So go on. Yes, what's the major product in this particular reaction? What's the name going to be? Do fast, put out the name of the major product in this particular reaction. The major product of this, remember, follow Z steps rule. I'm going to put out Z steps rule on the screen so you could see it. Z steps rule. Okay, no, you go block this thing. May you do sharp. We're going to end the class on this note though. Okay. Oh yeah. What is the major product of this reaction according to Z steps rule? Major product of this reaction according to Z steps rule. Times 3 into all. Okay, so let's see. Let's produce that. Now, first of all, is once you see this, it means that it's going to be, yeah, I forgot to mention that the elimination reaction of haloalkanes or haloorganic compound is what we refer to as dehydrohalogenation. So if you do not see elimination reaction, you can see it as the hydrohalogenation. Now, this is a lab preparation of an alkene. Just have that in mind, basically, that this is a lab preparation of an alkene or an alkyne. Once you're able to dehydrohalogenate, you make multiple bonds, and you can actually get your alkenes and alkynes by this process. Okay, let's get to work. Now we're going to remove, we have an opportunity to remove this and this, and remove this and this. Let's form the two of them. So if we're removing one here and one here, we'll have a bond here. The product is going to be C, double bond C, continue C, C, then OH was here, basically. So okay, that's 5. Okay, so OH was not there. OH is here and C. Okay, so basically we have that. this is going to be one hydrogen will have to leave here, and that is going to be CH2 instead. So H here and H here. Okay, let me put that on top instead. Okay, so that's going to be H here and H here, basically. And no chlorine here, one H here. Okay, and then this H2, and there is one H and H3. Okay, so let's see. Or you have another product where it was removed from this side and this side, which means there will be a bond here. So let's form the bond there. So that's going to be CH3 complete C, double bond is now here, and then you have C and then C, then the OH is here. Okay, filling the hydrogens, we have one hydrogen atom here, one hydrogen atom here, one here and three here. Okay, so if we are to consider the multiple bond is here, and you have this guy, just one attached to the carbon-carbon multiple bond. But in this case, the multiple bond is here, and you have one alkyl group on this side, one alkyl group on this side, which means according to Zaystev's rule, the major product is the one that has more alkyl groups surrounding it. So which means this is the major product, while this is the minor product. And with that said, if we are to name this compound, we are giving numbers from here: 1, 2, 3, 4, 5. This is going to be pent 3 in 2 all. Okay, we are going to be calling up the class at this point for today. Go up and read for other subjects basically. By our next class, we are going to discuss nucleophilic substitution and probably get into other homologous series. Thank you very much for joining our class for today.